Er is iets. Het is er nou met die teksten, dat is wel een paar fouten. Want er is een zwart vierkantje. Ik wil dat weg doen, dat gaat niet weg. En doe niks niet, dat staat een zwart vierkantje, oké. Dan, ja, op een deur heb ik de computer afgesloten, dan krijg je dat zwart vierkantje niet weg.
Over dergelijke dingen in het universum.
Ja, er zijn vreemde interacties, denk ik.
Hallo Paolo. Ja, is zo. Ik ga even kijken als we... Dus ik kan eigenlijk mijn scherm delen. Ja, dus dan zie je die teksten.
Ik weet niet of het dan nog, maar ja, we zitten natuurlijk vlakbij, dan zal het ook wel leesbaar zijn, denk ik. Je hebt een tekst, die de metalen doorgestuurd.
Ja, maar ik heb dat in... Hello Paolo.
Hello, that's okay.
I'm here with Professor Van Ostaaij, Fred.
Nice to meet you.
Pleased to meet you.
Nice to meet you.
Als we het nu een beetje hoger zetten, dus een beetje... kun jij eens praten, Fred? Kun je eens
Yes, what do I have to say?
een beetje luider praten?
Ah,
Can you hear it, Paul?
Can you hear me?
Yes, yes, it's okay. I can hear you.
Then I have to...
So where are you?
Rome.
Rome. Ah, good. Nice.
Roma.
So, how are you, Paolo?
I'm fine. I had some problem with my prostate. I have to make a surgery operation, but after Christmas holidays, I think.
Okay, so good. So we're going to because Fred is going to use the blackboard. So
Yes.
I have to use.
Yeah.
I can see the blackboard.
Yeah. So yeah, let's see. Actually, Fred was the first mathematician that I contacted with super ellipses.
Okay.
Yeah.
So
Is that the roots?
the roots, yeah. So
Yes.
was a bit a crazy idea, but
Okay.
Yeah, it was all about bamboo.
it was all
The
about
beginning, and then the voice. In fact, this model that I will talk about, you can give an interpretation as a kind of growth of a tree, if you like, or some structural growth.
So, just a moment. And wil je ook nog wat?
Wow, no, denk ik. Dat is veel meer toilet misschien.
So actually, I work in antenna company now, and the CTO and the co-founder is Diego Caratelli, and Diego was a student of Paulo.
Okay.
So that's how we got to know each other. Yeah. Most of the people in the symposium and last year also, I've collaborated with or continue to collaborate with.
Yes.
And it's a pleasant. So I only work with very nice people.
You make them nice.
No.
It's because of the cooperation.
Sorry.
You change them by the cooperation to be nice.
Yeah. But before I worked with some people who were more conflict-minded. No go. That doesn't work. So it's a waste of time. So yeah, but most of my collaborations are informal. So Paolo is retired. A few other Pino is retired. Pino Datoli, and a few other people. But our collaboration is outside of any. It's informal. So.
Yeah. Well, as long as it's interesting.
Hmm?
If it's interesting, it's good.
If it's
Or
interesting.
more important, doesn't matter.
Yeah, but in any case, all the presentations have a kind of mathematical component, but it's all about reality. That's the idea.
Yeah.
So I wanted to include more biology this time, but it was a bit. Yeah, well, some people could.
I have fiction biology, but
Yeah, I know.
the problem with this is that I guess it's sort of completely new, I can say.
Yeah.
And if I talk about it, I usually don't get any much further than the introduction and the beginning, so that they can understand the basic ideas.
Yeah. But I will start with giving an introduction.
Yeah.
A bit of an overview of what we've done last year, what we're doing this year, and then I will say how I see it a bit.
Yeah.
But if I start sharing my answer.
Maybe I will go to the secretary and have a coffee, a small coffee.
Yeah. Please.
Wake up.
So I'm sharing my screen now.
Mhm.
And how is Teresa, Paulo?
Yeah, it's fine. Thank you.
Yeah. So let's see who shows up. I don't know. I send a lot of invitations to people, so but let's see. But I'm going to record all the presentations so that people can look afterwards to them. This is Fritz van Ostaaien, a new generic model. It's very abstract, but let's see. Searching. It's always a bit of a question how many people will show up. So
Mhm.
you never know that. But anyways. Coffee. Ja, dat wordt eruit gegaan. Dat vorige week een afspraak met Anne. En ik heb, en ja, we gaan dat doen. Een espresso.
Ja, die koffie is goed. Er zijn alle soorten en allemaal staan.
Ja. Ja. It was Paolo was at La Sapienza.
Ja, en ook, maar ook Fiorentina zat in Ferrari. Maar dat is een bekende, dat was ook een Nobel zelf. Dat is een ander. Mario Fiorentina.
Yeah, Paolo.
Okay, yes.
Do you know perhaps Mario Fiorentini?
Only by name. I never met him.
I visited him a lot in Ferrara, but he was also a war hero. Several,
I don't remember. There is Fiorentini. There is. I don't remember. You mean Fiorentini? The studying algebra or something there? No.
Yes, algebraic geometry.
Oh no.
Was, I think, one of the first algebraic geometry, certainly in Ferrara. No, he was a nice man. Art critics. He was only mathematician. He started as a hobbyist. He was already, but in the university, I think he was already 40 before he entered there, and he was. I think maybe it was it Dieudonné, a famous mathematician from France. He said, well, you have Mario Fiorentini, and so then they hired him as a professor. But he was an art critic. He knows everything about film. He knows all the directors and so on. But he was famous for, and his wife also, Lucia Ottobrini was also one of the partisans. And they were.
Oh yeah, yes. Fiorentini, who was a partisan, I met him. I met him in Rome, but he's older than me. Older.
He's older, yes. No,
yes.
He died not long ago, but he was in his
yes.
90s.
And the teacher of Paolo was Gaetano Figuera, was also very famous.
Gaetano, yeah. I think, not by name also.
Yeah, so it's an interesting connection because Professor Figuera had very connections in Moscow, and actually Ilya Tavkelidze from Gielis will also speak today, also graduated in Moscow with Professor Oleinik.
Yeah.
And there was this collaboration, and I knew Paolo, and Paolo introduced me to Ilya in Gielis, and then we started to work together. Fantastic collaborations.
Yeah. Yes, you're also like a result.
Yeah. Like a rice.
It's normal. You usually have a worldwide connection.
Yeah.
It's mathematics, almost always, I think.
Yeah, it's a fantastic field. Huh?
Yeah.
And open-minded people.
Yeah, we are the real people. You don't see a mathematician bomb somebody in Gaza or something.
Well, some mathematicians helped in developing bombs.
Yes.
Mostly
physics, not mathematicians. So-called mathematicians, perhaps. Yeah, the physicist, you can give him a laboratory, he will do anything.
Yeah.
That's most of them.
So I'm going to
Yes.
The still persons are in the waiting room. Diego. Hello, Diego. Hello, Adia. So, is this now recording? Just a moment. Zoom. I'm just trying to see it is. Hello, Ilya.
Oh.
Well, Ilya is differential equation too, I think. So,
oh, Ilya.
Hello, Ilya.
Hello. Yeah.
This is Ilya Tavkelidze from Gielis. Diego Caratelli is spoke about him.
Diego.
And Paolo, and then we have
Ciao.
Aditya. I don't know him, not yet. So other people will show up. Still 12 minutes to go.
I was trying to check how the screen can go down. Is it here?
But we're let's yeah, I'm going to use this one. So Paolo, can I would like to check something.
Yes.
Going to use this presentation, And if red explains what do you see, what do you see now? You see my screen, and do you also see him?
Yes, yes, but very small.
Very small. Okay, so then we have to. But hoeveel moet jij vertellen aan het bord eigenlijk?
Dat hangt er vanaf. Ik kan er nu een kleinigheid opschrijven. Als ik die tekening heb, kan ik...
Die tekeningen heb je in verschillende slides. Niet overal, maar ik heb ze in verschillende slides teruggebracht. En eigenlijk staat heel jouw tekst erin.
Ja, ja, ja.
Uh-huh.
Ik kan er naar wijzen. Hè. Maar zie ik die ook hier? Gaan we die projecteren?
Nee, ik zou hier... Dat is share
oké.
screen.
Ja, ja.
Hè?
Ja, ik zou op de tekening, als ze dat kunnen zien, het is klein. Hè.
Ja, maar dat is voldoende groot hoor. Dat is voldoende groot.
Ik kan er naar wijzen. En dan
Maar anders moet je nu al een tekening maken. Dus, ja. Maar dus dat zij zien dat voldoende groot. Hè? Dus,
ja. Kunnen ze die lettertjes lezen die er staan?
Nee, dat kunnen ze niet lezen, dat moeten voorlezen. Dus,
ja. Ja, ik zal het zeggen. Maar
je hebt hier eigenlijk uw laag van uw tijd, hier uw laag van uw universiteit,
ja.
En hier uw laag van uw S en uw...
Ja, die heb ik amorf gemaakt omdat er geen structuur op zit. Dus die heb ik zo'n beetje...
Ja, natuurlijk.
En die ruimtes, ja, dat heb ik als boxjes getekend.
Nee, maar dat is goed. Maar ik heb jou gezegd ook van dat een geweldige figuur is. Dat stond in het boek Journey for Laughter. Zo'n soort of laughter.
Ja.
En dan...
Journey to the source of laughter. Dat was de eerste theorie nog niet helemaal af. En dan had ik al zo wat de filosofische achtergrond.
Ja, in uw boek van... And Matthew also. Hello, Matthew. Huh. Hello, Matthew.
Matthew. Ai. Ciao, Matthew.
Hello.
Ciao, Matthew.
Good morning.
Good morning.
Good morning. Hey.
Yes.
So.
Okay.
Just a moment. I'm going to. And Ian Mihai, so yeah, so this one. And then we have Ian from and Adela from Romania.
Okay.
So, yeah.
I have a lot of contacts in Bucharest.
Yeah.
With the algebra group of Master Cisco.
Yeah, okay.
We have a long cooperation. Many students from the Antwerp.
But yeah, you had Ian graduated with Paul Verstraeten in Leuven. And
good morning.
Hey, good morning, Adela.
Nice to see you.
Hey, hello, Ian. Hello.
Adela is teaching now, so
Okay.
I will be in the morning.
Okay, good morning. Good morning. So I was just telling, yeah, well.
Talking about Bucharest.
Yes, I am in Bucharest. Yeah.
Are you in Bucharest?
Yes.
I had a lot of contacts there with Master Cisco.
Ah, yeah.
Master Cisco. Yeah, and all their students. So Panaite, but Panaite is now in the English, I think, in the institute. But, there were a lot of students from Bucharest cooperating with us in Antwerp. We had a very regular contact. So, but only in the algebra direction.
In algebra, yes.
Hello, Pino.
Hello. How are you?
Hello.
Hi, Pino.
Hi,
Hello, hello, Pino.
Hi.
hello. Hi, everybody.
Ciao.
Ciao, ciao.
So here is a bit snow yesterday. It was snowing. There's a bit snow left now, but not too much.
Cold yesterday. No.
Yesterday was yeah, below zero in night. But
Minus
now it's
five,
like-
you say, -5.
Yeah.
When it's already
So-
better.
So minus is just well.
Yeah, it's just a zero. The zero has to be put somewhere. The cat is in South Africa. En die cat
Ja,
in
ja.
South Africa.
Dus er is een X-power, die is met exponential analysis bezig. En ik zit, dat is een Europees project. En ik zit daar ook in, maar ik ben daar een beetje tegen de rand zitten. In de zin dat ik een beetje breder kijk dan een exponentiële analyse. Je kunt in 10 manieren complexe getallen definiëren. Dus, niet alleen ons rekenen. How is your health, Ilya?
Me?
Ja, Ilya.
Ah, yeah.
So,
Also,
but better.
So
But better.
that means good, I presume. Huh? So,
Yeah.
um,
I am very glad to see every.
yes, of course.
Thank you, Johan, for this possibility.
this is my pleasure, truly. So Matthew Hay is the last collaboration of my mathematics. So they're all mathematicians, and I'm doing something. But and I met
With
Matt.
mathematics.
Hi, Nat. How are you?
Hey, how are you? Good morning.
What have you now?
It's 4 o'clock in the morning.
Oh,
Yeah.
Now, Ferrer is a student of Annie. So yeah, Matthew is the last mathematician that I met, most recent collaboration. And actually, Fred here is the first mathematician that I ever spoke to.
Oh,
That's super.
okay. When was that? When was that?
That was 1994, 1995, I think.
That late? No. My memory for dates is terrible.
Yeah.
I thought it was earlier, but
What? So about 30 years ago, almost.
Yeah. So
20 years ago.
I think I read about superellipses in 1993.
Mhm.
And then I thought about it, and I think I approached you in 1994. So, but yeah, he's a mathematician, very, let's call it,
Yeah, looking forward.
high-level algebra. So I was a bit nervous, but he assigned a student to do some calculations on superellipses and bamboo, and that's how it started. So.
Oh, wonderful, wonderful. So nice.
That is this Lemay, of which I didn't really know about it when you came to talk about it. But it was interesting because
Hey,
I found that it's kind of if you
read them out.
Hello, this.
if you take the one with the exponential e, the logarithmic ratio,
Yeah.
then you have a kind of situation where the flow around this form is maximalized.
Yeah.
And
Okay, that's written in this paper. but-
yeah. So, and you see it is sort of in fluids, when they move, you have a kind of thing that appears, these ellipsoids that appear
Yeah,
there of that shape.
but these Bernard convections.
Yes,
Yeah.
also. Yeah, but these hexagons. But I found that interesting, so that the bamboo uses that
Yeah,
to maximize the flow and so that it can grow fast.
we don't know yet, but there's just a few hypotheses.
Hypothesis, yes.
But it was more resistant to bending than posts.
Also, yeah, because of the flat point.
Okay.
Because of the point, the touch point, the flat point, flat point. German.
So it's about 10. We'll wait 5 more minutes, huh? And then yeah. Maybe dag verder. Ja, dat was eigenlijk.
Ja, wel, we zeggen dat lager allemaal.
Ja, absoluut. Welkom, welkom.
Ik weet niet hoeveel dat komt, wat was je?
Ik heb die presentatie, ja, dus. Ik heb eigenlijk, als ik uw presentatie laat zien,
Ja.
aan die eerste overeenkomst doen bij de Johan.
Ja.
En dan zeg je maar, dan klik ik elke keer verder en ga ik hier staan.
Dat gaat per bladzijde ook dan als je klikt.
Ja, dat is niet per blad, ik heb een beetje in boeken, dat leesbaar. Dus,
moet ik dan elke keer zeggen als ik denk dat of doe jij dat automatisch als...
ja, ik zie wat jij hier vertelt en zo verder. Dus, ja, ik kan dan hier staan, dus als Frits, ja, dan doe ik. Enfin, ik zal ik zal wel regelen, maar omdat je dan line of sight.
Ah, dan mag ik hem even plaatsen.
Yeah.
We moeten opletten, want ik loop gewoon als ik spreek. Maar al verder in en weer, niet beeld blijven.
Okay. Ga je uit de virtual room dan? Of niet? Nee, want je kunt niet zien. Hè? Matthew,
Yeah.
I have a question for you. So actually, I just got an email from the second speaker of today that he cannot join from China today.
Uh-huh.
And my question is, could you do your presentation as a second one?
Yeah, sure.
Okay, that would be great.
Yeah, I can do that. Yeah.
That would be great. Thank you very much. So these things
Okay.
happen. So
Yeah, sure.
okay, so I would like to welcome everyone. It's a true pleasure for the second symposium to see so many well-known faces. I've made a few slides as a presentation. I will share my screen. Just a moment. Erhan Guller is also here. So I'll have to take this into account. I have to share screen. Okay, so welcome everyone to the second symposium. So the first symposium was a bit of, let's say, an experiment, and I also chose a special name for it: square bamboos and the geometry, for various reasons. Because you want to stand out, and the idea is to combine people from various backgrounds, all having to do something with mathematics and reality as far as we can. So it's mostly on invitation of the collaborations that I work with. And most people always say yes if I invite them to speak, which is simply beautiful, which also shows the power of mathematics and connecting. So why is it called square bamboos? And why is it called the geometry? Geometry comes from a beautiful book, The Poetry of the Universe, by Robert Osserman, who was a geometer. And actually, Bennett Palmer, who will also speak today, was a student of his. He said we may picture the product of 3,000 years of geometric inventiveness in the form of a tree, the geometry, and its roots go back very, very long, representing centuries, millennia of discovery and creation. With or without application, the branches and fruits of this tree are worth contemplating as a remarkable product of human imagination. The geometry is healthy, vigorous, in full foliage, older than any redwood and fully as majestic. Beautiful quote, geometry. But on the other hand, there's also square bamboos, because that's where my work started. Let's say around 1993, I was reading about superellipses in a book of Martin Gardner. And actually, I looked I made the connection with square bamboos. There are 20 species of square bamboos in southwestern China. And then 4 years later or so, I could generalize this to what I originally called Superformula, to include starfish and various symmetries. But today is a bit of a special day. It's the second symposium. In 1994, the first mathematician that I ever spoke to, explaining these Lamé curves and this idea, was Professor Van Ostaaien. And he will be the first presenter. So it's a bit of a full circle. It's all, yeah, like almost 30 years ago. So we're getting a bit old, but but let's say the geometry is in full foliage, but also square bamboos opened a kind of new way of looking and studying natural shapes. I would like first to spend a bit of time on last year. Last year we had the first session of the Square Bamboo Symposium. We had, let's say, 20 to 25 people attending. And actually, the proceedings have been published last week. What is important for me is having these informal meetings, but also being able to publish these books in open access format. So it's accessible to everyone. Everyone can download it. As of today, I forgot last year because we had lots of Teams problems with Teams to record the sessions, but I will record now on Zoom, and then we can later put it on a YouTube channel if you agree, just for everybody to follow and know. But the written texts have been published last year, and we managed to have 3 sections. One was geometry, and I was lucky enough to have Bang-Yang Cheng as a speaker, which is recognized in the differential geometry quarters as one of the stars. Bennett Palmer, it was very interesting because he was one of the first to apply my formula as an example for constant anisotropic mean curvature surfaces, generalizing the soap bubbles to any, let's say, wolf shape or squares or prisms, and the corresponding catenowids and so on. There are 2 papers on the collaboration of myself and Ilya Tavkelidze and also Paolo. And this has to do with generalized Möbius listing bodies. And I will tell a little bit about it later. And then ongoing work by Ilya is trying to define what kind of shapes appear after cutting. And then we had also Rivas Grigolia about having 3-valued Gödel logic. And the background of this is that when we started working with supershapes and superellipses, to combine them in a geometrical way, you can do that via Boolean functions. But R functions, named after Ravchov in Kharkov, translated Boolean combinations into geometric language in a very simple way because it's very related to superellipses. And then, but you cannot only do that for Boolean logic, 2-valued, but you can do that for any partition on any, let's say, line. And then you end up with 3-valued or n-valued logics, giving more possibilities. So, and then there was also a session with more mathematical papers. But today there will also Paolo will speak tomorrow, and Pino will speak tomorrow, Giuseppe Datoli will speak tomorrow, but they will, this was about Laplace transforms and mixed differential equations and low factorial-based polynomials and umbral calculus. But let's say half a year after this, in July, we had also a separate meeting, and it turned out to be that many of these things could be related to studying the logistic equation. So there will be many talks having a differential, or let's say that having the logistic equation as a basis. So because we want also to have so mathematics coupled to something with reality. And then there was something, there were a few, I gave a talk, but there were a few people that applied superellipses in antenna technology and electromagnetic theory with Diego Caratelli. And also Bert Barings, he was actually, Professor Van Ostaaije Fred was the first mathematician I spoke to, and he assigned an informatics student doing computations on super ellipses and square mammoths. But later, Bert Barings was a student of mine and of Rudy Penne, which was a mathematician who was a student of Fred van Ostaaije, so it's a very short thing. And Bert was actually the first engineer that I worked with, and we have a long-standing collaboration of more than 20 years now. So which is, and I think that's very important to have long-standing collaborations. So what was interesting, here are a few summaries. Bangyang Cheng has many topics to talk about, but he focused here on the position vector in the study of manifolds, submanifolds in the sense of manifolds embedded or immersed somewhere, because it has to do with laws of growth in biology, position vector. Then Bennett Palmer discussed the construction of equilibrium surfaces, as I said, a generalization of soap films or soap bubbles. And then the generalized Möbius listing surfaces and bodies I will tell a little bit more about later. But one way to connect unconnected parts in the plane are so-called R functions. And it's really a very interesting and nice way to combine 3D or higher D manifolds into a, let's say, with any transition that you want, smooth or non-smooth. So this is this one. Yeah. Well, anyway, you can always look at all the proceedings are open access, so you can download them and read for yourself. Some of these things will come back later today. Sylvia could not join because, well, she's in the meeting now, but anyway. So, and then the super ellipses. As I said, Bert Barings was closely involved in the development of the Superformula. And I wanted to have him in the first meeting because I want to establish a kind of historical track record. Because if something is named after me, actually most of the things are done by others. And I want to acknowledge that. And that's the beauty of these collaborations. And actually, in my own article, I focused a bit on, if you look in a very simple way, if you look at the Pascal's triangle and take, not as we do in science, the probabilistic way of taking, say, the Gaussian and so on. But if you look at the outsides, the x to the end and the y to the end, that's exactly super ellipses. If you combine them via addition, and if you combine them via multiplication, you have all the power laws. And that's the beauty and the simplicity of it. Now we have a second symposium, and I would like to give a short overview of who is what. As I said, Fred van Ostaaije was the first mathematician that I ever spoke to. It was the reason was that I did my thesis in 3 Eiken, and his office was quite close to that. And so his office was the first, and I just entered more or less by accident. But I haven't spoken or seen Fred for like 20 years or more. He's somewhere in Brussels, I think. Could be. But anyway, a long time ago, until let's say half a year ago, I was on track of some new theories that he was starting to publish in books and articles and so on and so forth. His background is higher algebra and non-commutative algebra. Non-commutative geometry, which is far away from anything that I... Not so far. Not so far, maybe not. But anyway, then I started reading about this time hybrids, a new generic model of reality. And he will present this in a minute. Oh, there's Felix. And he presents this later. It's something that I like very much because I always think from how will we have our almost our theories of everything according to the physicists, which is of course a bit of to mathematicians a bit of nonsense, I think. But I always ask myself what happens in 300 or 500 years from now. So maybe they will laugh at us with our flat Earth theories or something that we don't know that. And Fred published something radically new, and he will present this. I hope you'll like it anyway. So then the second speaker we will move to tomorrow, but actually it's Matthew Hay will come into place. And then Ilya will speak about this cutting of generalized Möbius listing bodies. And then Eren Güler from Turkey, first time that we met, is also on the bridge now. We'll talk about helical hypersurfaces in four-dimensional Minkowski space. Next year, I also have already some speakers of high stature. Among them is Alfonso Romero, specialized in Lorentzian geometry and so on. So, but this is already close to this. Then an interesting one is wildfire propagation with wind and slope. And that has to do with Finstler geometry. Finstler geometry is, if we walk, let's say in kind of Riemannian geometry, we try to walk on a flat plane or a slightly curved plane. But what happens if you walk upwards with a slope? Then your, let's say, your unit circle is no longer a circle, but would be more elliptical. And I came into contact 5 years ago with Peter Antonelli, who was a geometer and topologist who spent a lot of time in finding applications for Finstler geometry. But he passed away 3 years ago, and also his wife Solange Roets passed away last year. So last year there was a conference in Antwerp on Finstler geometry, and it was also theoretical, except for one wildfire, and it has to do with what is called the Matsumoto metric. What happens if you walk up and down? And then another person that I met was Dave Thompson. He contacted me because he looked at model quantum systems as tools for learning and how the superformula can play a role in there, in the sense that if you want to study the movement of a particle in an isotropic space, that can be done. But what happens if you put a particle into a square box or a starfish? So we're just learning that. And then Bennett Palmer, as I said, a student of Robert Osserman, differential geometry, and let's say the shape of natural and abstract forms. He will talk about this later. I received this presentation, it's going to be wonderful. And then today, Matthew, he was scheduled to be the last, but he will be the second speaker. Actually, he will talk about human thought patterns. And that's something we are just exploring. It's a very wide and open field. Let's see what comes from that. So that's for day one. Day two will be related onto unusual exponential functions and applications to population dynamics. So we see more and more application of mathematics in our group to population dynamics and growth and so on. And also, because I'm involved in an XPower European project with Professor Annie Kuit, who does exponential analysis, she was very interested also to communicate, to connect with Paolo and Pino to see how exponential analysis and other basis functions could be expanded. And then tomorrow also Adela Mihai from Bucharest will speak, that based on a paper that was published this year about Pythagorean submanifolds. Very interesting paper, so that's tomorrow. And then Pino, it's Giuseppe Datoli, Professor Datoli will talk about difference equations and discrete logistic processes and algebraic ways to deal with that. And then there will be...
sorry, call me Pino. This is my favorite nickname. I don't want to be called professor also because I am not professor. So anyway, good.
Good. Okay, and then there was an interesting collaboration that evolved over the last, let's say, year. That's with Dominic Chapman. He's a sound engineer, a computer expert. And actually, he had already experimented with N-gun waves. And my reasoning was, in the Nanjing group, more than 40,000 specimens were tested with Superformula as a scientific method. So avian eggs, starfish, leaves of trees, seeds, and so on, and flowers. And then my question was, if we see that in shapes, should we not see that in natural sounds? And that's just an open question. So what we're doing now is building a library of sounds associated with super shapes, and then use these sounds to make some music. So it's very different from, let's say, the classical Fourier-like summation of synuses. And so it's a completely open new field. And it's also associated with a composer, Rexley Bunyard, who she has a perfect pitch, a perfect hearing, and she listened to all the sounds, and now she's trying to compose some music with it. So completely new. So, but in the end, we always started in the past. We also started with synthesis. So you type in some numbers and you get a shape. Then we moved to analysis. So you get a shape and get the numbers, and then look at optimization. And in this, let's say, sound phase, we're in the synthesis phase, and then we go to analysis. Hopefully, also with the people from XPower as more basis functions. And then there are two talks, one by Diego and one by Yvonne Wu from Delaware University. Delaware, Yvonne is also part of the XPower project, and she gave a very interesting talk about bones and bone structure and the fractional time derivatives that they use to model this. But that happens to be also fractional calculus was also used by Diego Caratelli and a few of other friends to model frequency dispersive dielectric materials, which could be skin or the cells and so on and so forth. So if we go back, for example, we see let's say in Paolo's and in Pino's talks, logistic equations, also in the talk of Pei Jiangxi. And we see here, let's say, also relations to skins and cells and bones. We see wildfire. We see elastic surfaces. That's also related, we'll show. And then, anyway, what I want to say is that in most of the cases, or in almost all of the cases, it's related closely to biological phenomena. Not always. Some are. Anyway, so what's the time now? So I think that was my introduction. So again, I welcome all of you. And now it is my true pleasure to present Fred van Ostaaien. He has been a full professor here at the University of Antwerp for many, many years. And as I said, is the first mathematician that I ever talked to. And he will not be the last, of course. But he is going to talk about this new theory of new generic theory of reality. And I first have to then share my screen. You are all seeing my screen now? Yeah. So, okay. Okay. We'll stand here.
Well, thank you, Johan, for the invitation and the opportunity to talk about this.
Please a bit louder.
Yeah, I will talk about the growth of the universe. So the growth is in it.
Yeah.
And of course, Time Heinrich is this book, Time for Advertisement. And it comes from my work on non-commutative geometry. But I will not insist too much on this in the talk. It's technical. Even in the book, I only mentioned it because the book was aiming at a more broad public. Okay, so let's begin. Growth suggested a process. Everything will be processes. The Greeks already said pantarai, everything flows. Everything will be a process. And the most important thing to do is to define time. Now, if you ask a physicist what is time, you will get a very unsatisfactory answer. Time is what the clock measures. They have no other answer. They have other things to say, but usually that doesn't stick. So, but of course, is that true? What does the clock measure? The clock measures a movement. Planets move, moon moves, Earth around the sun, some vibration in a crystal, what else? Atomic movements, atomic clocks. The more tiny you go, the better, it seems. But that is all distance, right? And if you light here is also distance. So this is not time. What you then measure is a sort of an effect of time. You use time in some way, but that is not time. So what I wanted to do is to give a generic theory. And what does generic mean? Generic means that it has the minimal assumptions. That I don't want to assume on reality things that I force. I want to describe reality. Therefore, I have to stick to minimal assumptions. So one of the things I will not do, but you can do if you want, is to use numbers and measurements with numbers. Because another thing you can ask the physicist is, why do you think that everything can be measured by real numbers times a unit? And they have no answer. They say, well, it works. Yeah, of course, the real numbers are complete. So you have convergence of sequences. And that is nice for physicists. But there is no reason for that. There's even no evidence, and it's not even plausible. So I don't want that. I don't use numbers. If you want, add it as an extra assumption, then you can do it. So I will start with time. My definition of time is very simple. I say, okay, time is a totally ordered set. And that's all I will use, because in the description of the universe and the reality, you want to use something like cause and consequence. But what is essential is that one is before the other. There will be some comments about that later too. Some physicists try to use the future to define the now or the past. But there will be some nice, elegant answers to that. Anyway, so totally ordered means that it's a partial order. Just think of an order if you want. And for every two elements, one is before the other, unless they're equal. So one of them is the first and the other one is the second, unless they're equal, and then they're equal. So what is, for example, time? Well, I will draw on the blackboard, or you can see it. Time is, for example, here. I draw it as a plane, but it can be a vector space, positive part of the real numbers. It can be a Euclidean line. I really begin to like Euclidean geometry much more now, because Euclid, he doesn't use numbers. Paradoxus introduced some approximation of real numbers, but it did not introduce real numbers. But Euclid uses a compass, the width of a compass. And then the Euclidean line is a totally ordered thing with an addition. And the addition comes from the fact that you can put it's one of its axioms, you can put the compass in any point and draw a circle. So you can measure the width. But the width is not a number, it's the width of the compass. There's no number there. So this Euclidean geometry is a very nice example of something that looks like a line, the Euclidean line, and you can use it as time. It's totally ordered, and it has an addition. And if I want to assume anything more than the total order of the time, then it will be an addition, but not a field of numbers or a vector space or something. So that is essential in having cause and consequence later, but there will be a lot of things to say about that. This will not be so beautiful as you think it is, because there will be observations, existence, and reality. So there are three things, what I call reality. Let's see what that is. Then I call it existing reality, and the observed reality. These are three different things. They're not the same. They're very different. Even the existing, it's different. So we have the definition of time. This I will have to define also existing. And this is something that they don't do in physics. They assume that we know what existing means, but we don't. So I have an axiomatic definition in the moment. And then you have a combination of time and existence, and then you go to the description of reality. So, okay, what about this existing? I have only time at the moment, so in every moment, I take the moment t. Time is a set, and I call it the elements moments. And in every t, I assume there is some space, something, not a space, a state of the universe. U of t is a state of the universe. What is it? Well, it's a state. And I want to give it a geometry. Although nothing will exist in a state of a moment in the universe, there is nothing that exists there, because in existing, the definition will be that it's something. Intuitively, you can already think that it's something that is present in a certain non-zero time period and in a certain place. Yeah? I don't know yet which time period, and I don't know the notion place yet. So I have to define all this axiomatically, and without making too much assumptions. I don't want to say it's a manifold, something like that. That's too far. That's just our model, which we have, that we want to force on reality. That would not be generic. So I will go more simple from the beginning. So I take just a set and with a non-commutative topology. Here is already something. But this is the weakest geometric structure that I can think of that you can impose. But this is only on the state. The state is something abstract. It does not exist. There is nothing there that exists. But there will be some other things, because I have to explain how things become existing. So I will have here the elements. There will be something above it, potentials. So they are here. I will introduce later some set ST potentials. I also call it pre-things. So they are not things, they are pre-things. That means in some process, they will evolve to existing things. And the process will be on a certain time interval. So I have to look at, in prime, I have t prime. So I have to look at intervals t prime. And I will only look at closed intervals. That's an assumption. So I will look at the interval with including t and including the beginning and the end. The other intervals can appear, but these are essential for defining existing in a moment. Okay, so now you can say, well, but you choose some strange geometry here. It doesn't matter. If you want, you can take Euclidean geometry. What I will do is get a dynamic theory. The geometry will become dynamic because there will be movement and so on. So there will be a dynamic geometry, and so this will lead to a dynamic, non-commutative, if you like, geometry in a way that I will describe. I have to define places before them. But the fact is that if I choose another geometry, everything works. Everything works, but you will get this dynamic Euclidean geometry, dynamic differential geometry, dynamic, whatever you choose there becomes a dynamic version. This has not been studied in mathematics. This is a geometry that changes. It is not a movement in the geometry. It is really another geometry in the states, and it changes in time. So what the physicists, they use always the same geometry. They take a manifold and they think everything is destroyed by this manifold. There's no reason for that. But if you want, you can do that. You can say, okay, I want a continuous thing, or I want a fixed geometry. But these are extra assumptions, so I don't put them in my generic theory. This dynamic geometry, you have to compare to reality. And here you can say as a physicist, okay, maybe I can do some experiments. You can. So if I take Euclidean geometry, I get some dynamic Euclidean geometry, And you have to see that it fits your reality, your observations. So you want to use the observations to say that, well, I like this description or not. If I would find things that contradict the observations, then I would say, oh, my geometry was not right. Now, with this, there is no danger of having contradictions, because it's really the weakest. You should think this is like just having a topology, but not on a set of points, but a lattice, a non-commutative lattice, or a Heiting algebra, if you know that word. So this is in terms of lattices. Non-commutative lattice even. So it has a join and a union and an intersection, a join and a meet. But they are abstract, they're not on points. So it's an abstract definition of a lattice. And the thing that is, for example, in Hilbert spaces, you use that and so on. The quantum sheaves are on lattices. So quantum theory also changes from topological lattice or sheaf theory. So there's a good reason for all this, even in the actual physics. So I will not have time to explain everything, but that's a step which is, what I say generic for the theory, it means that relativity theory and quantum theory fit in it. Because I have the weakest assumption possible, if there would be a contradiction, also relativity and quantum would be wrong, because they are stronger. They assume more than what I do. So I'm not going to claim this is a unifying theory, but it's a root of both theories. You can use this as a
I apologize, but maybe there are problems with the microphone.
Okay, you don't understand too?
No, it's hard. It's not clear, like when you speak. Maybe it's far away from the microphone.
Ja, ja, dat weet ik.
maybe I should turn around.
Misschien kun je gaan zitten en minder aan de boek en gewoon met zijn presentatie gebruiken.
No, I will only write on the blackboard when necessary then. I'm closer to the mic now.
Dus dan moet je gewoon hierop drukken om verder te gaan. Dat zal ik wel doen.
Ja, ik hoop dat ik het kan vinden. Ja, okay. So is it better now?
Better, thanks.
Okay, good. So I'll stick here now. Writing on the blackboard is maybe too bad here. Anyway, so now I gave a lot of lectures in Sweden and England to physicists about the non-commutative geometry, and I first wanted to explain a geometry for the universe. Not really so ambitious to say that a reality. Many quantum theorists were interested, and they asked, yes, but how can you describe the events in the space? And so the physicists, they have no problem embedding the reality in their geometry, which is of course wrong. You cannot embed reality in the geometry. Like a geometry is an abstract thing we construct. It would be a bit godlike to assume you can embed reality in it. So what I wanted to do is to define reality over it, like a sheaf theory. You have an étal space. I will define a space, but it will be over the space. The things will be over the space, not in the space. So I said on the text, you cannot embed an elephant in your geometry. Stupid. In fact, I will not use points and numbers, so and also not equations. And as I said, if you want to, you add this as an extra assumption that your structures have a real structure over the real numbers, but I will not do that. So if I now push here, is that going to be further?
Yeah, this.
Oh, this one, yeah, okay. So this elephant cannot be embedded. So now I have to define the potentials. If somebody knows sheaf theory, then you have an étal space over some topology, and then you take direct limits for the points. And then you have the stalks, and in the stalks you have some elements, and you have germs of functions. This word germs is interesting here because I want to describe the growth of the universe out of the momentary pre-things. So this is the only assumption I make, in fact, that there is momentary things. Newton also had momentary interactions, but he assumed that they existed. And then you have existence in moments, which is leading to lots of contradictions. So we don't want that. But we have to have existence in intervals, and we have pre-existence, if you want, in moments as germs, potentials. So this is logical that when you go to a moment, you lose the existence, if you want to think in limits, let's say, but you keep the potential of the existence. That's the reason I call them potential sometimes. But I will also, in the book, I use the word pre-things, and then I will use pre-interactions, pre-objects, pre-events, pre-energy, because when you know that it evolves to an existing thing, and the existing thing is an electron of energy, an event, a black hole, whatever, then you can transfer this property to the name of the pre-thing. Now, I know that at the moment that I'm looking at these things as pre-things, I do not know what it will become after the time period passes and it evolves to something existing. So I don't know that it will be an interaction, yet I call it a pre-interaction as I act as if I know. It's a little bit like playing Zeus in Euclidean geometry. When you do the congruence relations, you act as if you know to move things in the plane. Well, you just think that you can give this name, but it's only linguistics. This is not related to the mathematics. So, okay, so now I have to, no, I'm not right. It's on the paper, you can read it. There is a set ST, which is defined over if you look on the drawing, you see the plane T, and in every moment, you see the UT is like a cube there. That's the space. Well, not yet, but it has a geometry and so on, a topology. And above it, you have a set ST. You also have ST is just a set. That's why I draw them very amorphic on the drawing. I don't have a structure there. It's abstract. They're potentials. But I have a place map. And this is like in a sheaf. When you have something over a topology, you have a map going to the topology. Well, here I have this place map, which is, I didn't have the pi on my computer, so I used this strange sign, double S or whatever it is. And so I look at sets of potentials, AT, with small letters I will mean the elements, and with big letters, sets of. And the AT has a place, and that's the union of the places of the little a's in it. So that is the join in the non-commutative topology. It's not the union, it's the join, there are not points there. Anyway, so I have an image of an AT in the cube. You see I draw there PT, and the drawing is also, this gives the shape, in fact, in the UT. But the UT is in a moment, remember, so we cannot observe that. Now I have maps from the UT to the UT prime. If I look at another moment T prime, as I draw on the blackboard, maybe I will draw one thing more on the blackboard here. I draw here UT prime, and T prime is bigger than T, let's say. And then I have a map from UT to this. I have a map. You have to think that the states are the pages of the universe, of the book, and I have to glue the pages. So first I have geometric maps on the UT, and I call them FTT prime. I don't know why it here. FTT prime. And the condition is that if T prime is T, then FTT is the identity. And if I have two, if I have a T prime between T and T double, then the composition of the two is the map from T to D double. So that is the kind of consistency that it doesn't depend on the intermediate state. Okay, on the drawing, you see these red lines on the level of the UT, those are the Fs. So that means that if I have a place of an AT, it also has an FTT prime to the place of AT prime, but there is a problem that the place of AT prime is not the same as the image of the place of AT. And the place of AT prime is another one. And you see that there's another in the second cube, you see the other place. And there is a difference. And the difference is meaning that there is movement. So you have to think a while about this, that when I have to compare different states, I cannot compare them. You cannot compare the states, they're different. That's a problem. But with these geometric maps, I follow one place to another place. And the thing that is in that place, if there is something there, it would be standing still. I mean, the maps just tell you that you go from one state to another, and there is no way to compare the places, except if there is these maps. And then the image of the place is, in fact, identified to the same place. Later, when we observe or when things exist, all this is invisible. It's in moments. So in the drawing, you see the difference between the image of the place, AT, and the place of AT prime, which is something that will correspond to this. In a moment, I have to explain that. Then this is a difference, and that's the movement. So where does it come from? On the level of the STs, which are over not in the UTs, but over the UTs, I have also some kind of maps, ST, T prime. And they are correspondences. If you mathematically know what that means, a correspondence between two sets is just a map on the set of sets of these. That means it maps a subset to a subset. That's a correspondence. Well, something happens, but I get the picture of the university, but I don't know why. Connect to UA guest. That's something, somebody joining us, or it comes again. Okay, so I have these correspondences, and they also satisfy the same little axiom that